Okay, so yeah, today is the day for the midterm, but you can turn it in just whenever. I don't care. Preferably if you could scan it. I don't know if that's. I'll give you an extra day or two if you can scan it, send it to me instead of handing me paper. Is that cool?
Okay.
Yeah. That way I don't have to carry around a bunch of papers. Okay. Are you enrolled in this class? You're not. Okay. I could, because you asked me about something about the midterm, and I started thinking that you were enrolled. All right. I don't know where I'm at. Anyways. Okay. So yeah. So just turn it in whenever. If you have questions, probably because what I'll do when you send it to me, I'll look at it, and if I see something wrong, I'm going to send it back to you and tell you what's wrong and how to fix it. Okay? Because I'd rather you get it right than have to fail you. Okay?
Appreciate it.
Okay. So last time, not many of you were here, but we talked about normalizability in a more general sense. Can you guys see all right if I keep those lights on? I think we keep those lights on, right? So what we were doing was basically talking about divergences, right? And up to this point, we had really only talked about divergences, on a diagram by diagram basis, right? And then we talked about how to normalize these things. But what we were after in these lectures was kind of a way to, to look at a theory, not a particular diagram, but to look at a theory, like just look at a Lagrangian and be able to say, this theory is normalizable. We're going to be okay. We can introduce a finite number of counterterms, and as we go up in perturbation theory, be able to normalize this thing. Or the other case, we can look at the theory and say, we're going to be in trouble. This one's non-normalizable, right? And so that means that there's no finite set of counterterms that we can introduce that's going to keep this theory finite, right? At some point, it's going to blow up. And I made a point of saying, that even if a theory blows up, or if it looks like it's going to blow up, if it's not normalizable, that doesn't necessarily mean it's garbage, right? So effective theories are very useful in describing physics at low scales. Obviously they blow up, or their feature is that they blow up at higher scales, but at lower scales they're good, and they're non-normalizable. So they're a perfect example of non-normalizable theories, but they're not garbage. Okay. So we started by saying, okay, let's look at the most general theory we can, right? So we wrote down a general Lagrangian, and we included all vertices, right? So from n, where n is the number of external legs on your vertex, so from n to infinity. And what we were after was kind of a generic or general way to kind of say if a theory is normalizable or not. So we introduced these shorthand notation for number of external lines, number of internal lines, number of closed loops, and the number of vertices. And we wanted to ask ourselves, do momentum intervals from a particular diagram diverge, and if so, can they be normalized? But we had been doing that already, right? We'd already started this kind of power counting thing. When we looked at a particular diagram, and every time we had a closed loop, we said, okay, at a closed loop, we have a factor of momentum coming in from the integration, right? We have d. If we're working in d dimensions, we have d factors of momentum. Internal lines, we get 1 over p squared or 1 over k squared, however you want to write your momenta. And so those are coming in at -2 factors of momentum. Yeah. And so we said, okay, so from this, what we're typically doing is we look at the numerator, we look at the denominator. If the difference between those two, the factors of momentum, is greater than 0, then we say, okay, this diagram is finite, right? But if it's equal to 0 or less than 0, we expect divergences, and that's what we've seen in every case, right? So in terms of those the shorthand notation, that shorthand notation I had introduced on the previous slide, what we're basically doing is saying we're defining something that we call a superficial degree of divergence, right? And so the degree of divergence is the number of closed loops you have times d, that's that factor d up there, minus the number of internal lines times 2. And that 2 is coming from the p squared, okay? And so what we did was we had one loop, and we had, I don't know, let's say we had the self-energy, right? The self-energy guy, we had something like this, right? So we had one loop, and we had 2 internal lines. So that meant we had d minus 4, right? Am I doing this right? Yeah, d minus 4. And so we want something, that's not correct, right? We have d, because we were working at 6 dimensions. 6 minus 2. What am I doing here? Oh, no. Yeah, if d is greater than 0. Sorry, I'm saying that backwards. If d is greater than or equal to 0, it diverges. If it's less than 0, then it's finite, right? Because you have more factors of momentum in the denominator, right? So as p goes to infinity, the diagram dies off. Right? Whereas if you have more factors in the numerator, it blows up. Sorry, I'm just getting ahead of myself, okay? So we see that in dimensions 4 or greater, we're going to have a divergence from this guy, right? That's what we, that's what we kind of determined a while ago, right? And so what I wanted to do was, so that was, for one particular diagram, that's what we've been doing, and I want to try to find a way to do this for a general theory, okay? And so we're going to work with our theory that Lagrangian that I wrote down that includes all vertices, okay? And let's say we have a loop diagram or some process that involves E external legs, right? And so one of the contributing diagrams to this is going to be our tree level diagram, right? Our tree level vertex, because we have all vertices included, right? And we ask ourselves, what's the mass dimension of that diagram? Well, that diagram is, the Feynman rule is just minus I ZE times the coupling GE, right? And ZE, those guys don't have mass dimension; they're just constants, right? So that means that the mass dimension of our tree diagram is just going to be the mass dimension of the coupling, right? But we also have, in addition to these, we have loop diagrams contributing to this that are made up of, diagrams that include other vertices, right? Vertices less than E, right? You guys understand what I'm saying? So if we had, so let's say we were, let's say we had something that, we had some process 2 to 2, okay? And let's say we have a theory that has a phi to the 4th type of interaction, something like in the midterm, okay? So we would say, okay, this is made up of the tree level, right? But we would also have phi cubed interactions. So we would have a contribution to this guy that, let's say at loop level, would look like this, okay? So this involves loops, but it involves the vertices that contain fewer legs than this guy. Does that make sense? Okay. So that's what I'm trying to say at this thing. All right, so we have loop diagrams, and when we consider, computing this thing completely, but we know they have to have the same mass dimension as whatever the tree level diagram does, okay? And so that tells us that the loop diagram also has mass dimension of whatever the coupling is. And a loop diagram, as we've seen, is made up of the mass dimension of, its components, right? So in this general case, we have the D times L minus 2 times I. That's just the normal one we've had. But we've also got an extra piece coming from these vertices because we don't know what the mass dimension of these vertices are. And so we can put that together and move some stuff around, and we can find, using our expression from earlier, because those first two terms are just what we call the superficial degree of divergence, right? And we find that we can write down a formula for this guy in terms of the model parameters, so just the couplings, right? Okay. And so this is a nice thing to have, because now we can say, okay, looking at a theory, what is it going to be divergent or not? And the way you can see it is, so degree of divergence, make sure I get it right this time, is if it's 0 or greater, it's divergent, right? Okay. So if we have one of these guys, at least one of these guys that has mass dimension of a negative mass dimension, right? That's going to ensure that we have, because this guy's already out here, so that's going to ensure that we're going to have some, a superficial degree of divergence that's greater than 0. Everybody get what I'm saying? Okay.
As we increase
because we increase, yeah.
As we increase,
right.
Increase the resistance.
Yes.
At some point, we are sure that happens.
Yes. Yeah. Right. Okay. So in general, you can say, and that's why I put it in this box, that if you have a theory that includes any interactions with negative mass dimension couplings, in other words, the mass dimension of the coupling is less than 0, you say the theory is non-normalizable. Okay, and that's why I wrote down the example of phi cubed. So our 6-dimensional theory. All right, we had for the interaction parts, which I'll call it L1. We have this one, phi cubed. This is the one that we always talk about, right? And let's say we wanted to add a phi to the 4th interaction. Okay, so we're in 6 dimensions. Let's see is this the one I wanted to work with? Yeah. And we want, so we want the Lagrangian itself to be have dimension 4, right? Shit, you guys got to help me, man. So we want this to be 6, right? Is that right? Yes?
I think so, if we're in 6 dimensions, because
Yeah, the Lagrangian.
yeah, because the action has to be 6.
The action has to be dimensionless. Right? And the action is the integral of the Lagrangian. This carries mass dimension minus the d. Yeah. So this is 6. So this carries mass dimension of minus 6. So yeah, so we want this guy to be 6. Okay? So what does that mean? So that means from this term that our fields, or from the mass terms, we determine that the fields, the scalar fields, have mass dimension of 2. Right? I think we did it in general, right? But if we look at so if I have, so those guys go like phi squared, right? One's the mass term and one's the kinetic term. And if that has to be 6, then that means that the mass dimension of the field itself is 3, right? So in 4 dimensions it would be 1, but here at 6 dimensions it's 3, right? So that tells me not 3. 3?
Yeah. Because we also have that ms squared.
I have.
ms squared.
Oh, yeah. Yeah. So that term is m squared, phi squared, right? So that kills off 2. So it's mass dimension 2, right? Yeah, that'll buy. All right. So let's look at our phi cubed interaction. Okay. So our mass dimension of our field is 2. So that means the mass dimension of this whole term is 6. All right. That's what we want. So that means, or this term is 6, right? Mass dimension 6. So that means the mass dimension of this coupling is 0. Okay. Now let's look at this term. If phi has mass dimension 2, that means that this guy has mass dimension 8. Right? So that means that this guy has to have mass dimension -2. Right? It has to go something like a 1 over mass squared. Right? And so it has a negative mass dimension. That means this theory, if I include this phi to the fourth interaction, is non-renormalizable. Okay? And that's why when we consider phi cube theory, we don't have a phi to the fourth interaction because it's non-renormalizable. Okay? All right, makes sense? Okay, so that's an example, a muddled example, but thank you for helping me work through it. Okay? All right, so you can work it out in general, and I should have just gone to this slide, but it shows you that in 6 dimensions, any couplings, so for n, that n is the number of external legs, so if you have any vertices that have more than 3 external legs, theory is non-normalizable. Okay. All right. So in the end, we summarized and said any theory is non-normalizable if any of the coefficients of any term of the Lagrangian is negative mass dimension. Okay. So that gives you a way to look at a theory and do what we just did, but hopefully do it in a more efficient way. Okay. And then we just talked about the 2 point. So we said, you could consider our 2-point diagram as a 2-point vertex, and we showed that what the mass dimensions of these counter terms are. Okay, it's no big deal. And then we said, okay, there's some special cases where this superficial degree of divergence doesn't work, right? So we're saying that when d is less than 0, we should have a finite diagram, right? Well, it turns out that that's not always the case. Okay, so you can have cases where d is less than 0, but you have divergences, right? And that would be in this case, right? So this is a loop level correction to already a loop level diagram, right? So this is at 2 loops, but it's got this self-energy insertion is what we would call it. We know that this diagram has divergences, right? Right? It's the self-energy diagram, just this part, this guy right here, okay? And so that diagram has divergences, but we know that anytime we see that insertion, we have to include this diagram, which is the counter term. Okay, so even though we would compute, the superficial degree of divergence of this diagram, and we would say, okay, it's less than 0, so it should be finite. But we compute it, we find out that it's divergent. Okay. But we're okay because we always have this counter term, right? And then there's another case where even if we compute a diagram, we look at a diagram and we say, the degree of divergence is greater than 0, this diagram is going to be divergent. And then we compute the diagram, we find out it's finite, right? And a perfect example of that is in QED. And what happens there is in QED, your propagator terms aren't just like 1 over k squared minus m squared. There's some stuff in the numerator, some factors of momentum in the numerator. And that's what bumps up your degree of divergence to give you a greater than 0 degree of divergence. But what happens is when you compute that the numerator and you simplify stuff out, a lot of stuff cancels out, right? And so you can still have diagrams that have a superficial degree of divergence greater than 0, but are finite. Okay. So it's not it works pretty well, but there are some exceptions. Okay. Okay. So I think this is where we stopped. Okay. And what I wanted to do was just, very briefly, kind of work out a recipe to compute diagrams to any order or process to any order. Okay. And so the way we do this is, there's, one way, which is kind of the dummy way, which is what I would do is if, somebody said, go compute this process to next leading order. I would go and write down the tree level diagrams, and then I would go and, add whatever loops I could, right, to those diagrams and compute those loop diagrams. That's what I would do. But there's a smarter way to do it. okay? And the smarter way to do it is to go ahead and compute your kind of fundamental pieces, right, to all orders, or to at least to the higher orders that you can, right? So the first example would be the propagator, right? So go ahead and calculate the contributions to the propagator, right? And that would be your propagator that you would use in diagrams. Right? And then you do the same thing for, say, our phi cube theory. You would go and compute the corrections to the 3-point vertex. Okay, you would have that already in your hand. Okay, and then if you're interested, whatever process you're interested in, most of the time we'll be interested in the 2-to-2 processes, right? You would go and compute whatever loop contributions there are to that, right? So in our case, we had, well, I don't have it up there, but the box diagrams, right? So we would have those. Okay. And this is assuming, so anytime I have these shaded blobs, I'm assuming, or it's defined as to all orders, the exact propagator, the exact vertex. Okay, but that's that's la la land. We can't do that. Okay. Yeah, right. It's to all orders, right? But that's not possible. Okay, but we can still dream. Okay. All right. So let's say we're interested in, we have our phi cube theory. We want to compute 2-to-2, and we want to compute it to the highest, or the most, the highest order that we can. Right. So out to several orders of perturbation theory. So what we would do is we would write down the 2-to-2 diagrams that we had before at tree level. Right. Well, and this one included. But we would replace, everywhere we had our propagator, we would replace it with the exact propagator. And everywhere we had the vertex, we would replace it with the exact vertex. Okay. And then that means that we would also have to include this guy, because we know that it comes in at loop order. Right? It comes in through that box diagram. Okay, and at that point you say, okay, this is the 2-to-2 process to all orders. Right? And then you have to come back down to earth and say, okay, how high can I compute this? Okay, and so this is, I think I've talked about this before, but this approach of taking the Born, or the tree level diagram is also called Born diagrams, Born level diagrams. But this is called dressing the Born. So you take the Born diagrams and you dress it with blobs. Right, and those blobs are the exact either propagators or vertices. Okay. So this is how you would do it in real life. Okay, so we have these diagrams, right? And what I want to do is show you how to do this. Okay, so at lowest level, we would have the tree level diagrams. Right, we've already computed that. This is the sum of 3 terms, right? That are just the propagators, and our arguments are the Mandel-Salmon invariants. Right? Okay, so now we want to compute this thing to next deleting order. All right, so first we look at the exact vertex, the exact propagator, right? And remember, it has this form, looks like the tree level piece, but the correction comes in as the self-energy down in the denominator, okay? And that self-energy we've already computed, okay? So we said, okay, well, we know what the self-energy is because we, when we started with this theory, we went ahead and renormalized it and did all this stuff, right? And we got something that looks like this, okay? If you go and compare it to what we had before, it might look a little different, but it's the same. It's just that I think we did the renormalization. When I wrote this down, the renormalization was done at a different point. So it looks a little different, okay? But it's the same. All right, so that's that. All right, we can do the same thing for the exact vertex. Right, the exact vertex, we've only worked out the next leading order, like we did the propagator. Right, and we found something that looked like that. It was 1, well, it's the vertex divided by the coupling. And it's 1 plus some order alpha correction. Right, alpha being g squared. Okay, and this is where we left it, right? Because we said we're going to just use numerical techniques to do that, right? To do that integration. And then finally, we had the 4-point correction, those box diagrams, and we found that they basically took this form. There's three of them, right? One depends on S and T, one depends on T and U, and the other one depends on U and S. So remember, we computed one of these, and then we noticed that you can get the others by just switching the momenta, okay? Okay, so we have expressions for everything that we want to next to leading order, right? So for the vertex and the propagator and that, the correction to the vertex itself, the 4-point vertex. Okay, so we want to start with our tree level diagram, right? And we're going to expand out, for example, this guy. Right? So we want to work to some particular order. Right? So the way we would do that is we're going to take each of these guys and we're going to expand them out. We're going to plug in our exact expressions and expand them out. Okay. So you have one term that's basically the vertex corrected, the first vertex. So this is just the S channel diagram. You have one diagram where you have the propagator and then the other vertex. Okay, and this is what you would get if I just sat down and started drawing loops, on the tree level diagram. But this is kind of a more elegant way of getting to that point. Okay. Okay, so what we're looking at is we want the total amplitude, right? So the total amplitude in perturbation theory is going to be the tree level plus the one loop corrections. Okay, that's the amplitude. We still have to take that amplitude and square it. Okay, and in terms of our exact propagators, if you want, you could write them in like this. You see, this is the S channel, T channel, U channel diagrams, and then finally the 4-point vertex. Okay. All right. So I say we want the total amplitude, and we want to square it. Okay. So I square it. I get the tree level piece squared, which is what we would have computed before. It's a tree level amplitude. We get the cross term between tree level and one loop, and we're taking the real part of it. Right. And then we have the one loop squared. Right. The one loop squared is a part of the next to leading order corrections, right? If you count the couplings, so here this is like G to the 4th, this is like G to the 6th, and this one would be G to the 8th, okay? But it's only part of the story. There's a lot more that contributes at G to the 8th. So what we're going to do is drop it, okay? We're saying it's only part of the next to leading order correction, so let's drop it, okay? And we'll stick with those first two terms, okay? And like I've always said, once you get to this point, that's when you plug it into a computer, okay? If you want to stay with everything exact, if you want to keep all the masses and keep everything exact, you have to do it numerically, okay? But we can work in what's called the high energy limit, okay? And this is actually the case of, say, the Tevatron, which is now shut down, or the LHC, where you have energies that are much higher than the particles that are colliding and the particles that you're producing, namely the quarks and the gluons, right? Or if you're at a linear collider, maybe you're colliding electrons, right? And so the mass there of those guys is going to be negligible compared to the energies involved, okay? So what you can do is you can basically take the mass goes to zero limit, right? And a lot of those expressions simplify, okay? So for example, the self-energy becomes that thing on the top line, and that thing on the top line I can actually integrate if I use Mathematica, okay? And I get something that looks like the equation 23, right? And so that means that I can take my self-energy now, I can plug it into my exact propagator, and I expand it out, right? And I get something that looks like this. So I get an analytic formula now for my propagator, okay? And I can do the same thing for the 3-point vertex, and I can expand it out, okay? Now you're saying, wait a minute, I thought we took the m goes to zero limit, right? But you still see these logs that have m in the denominator. Well, these are going to be important, okay? We can't obviously set m equals to 0 in these guys, because what happens? they blow up, right? So for the time being, let's keep the masses in those terms. We'll set masses to 0 everywhere else, okay? We'll come back to those guys, all right? And then finally, I can even do the 4-point vertex analytically, and I get something that looks like that. It's pretty simple looking, really, right? Okay. Right. So I can put all that stuff together. It's just a few expressions now, and I can write down the whole one loop amplitude on one line, an analytic expression for the whole one loop amplitude on one line. Or I'm kind of cheating because I'm calling F for this. Okay, so it's maybe in reality it's a couple lines. All right, but it's a nice compact expression. It's written in terms of your invariance and then that leftover mass that we talked about. Okay, and what we see is that the tree level the tree level amplitude is corrected by powers of logarithms. Right? And these logarithms depend on kinematic variables. And this is something that you see no matter what theory you're working in. So if you're working in QCD, the leading corrections are always going to be these logs. Okay, these logs, because they're going to be logs of big numbers. Right? And logs of big numbers are big numbers. Okay, and so those are always going to be the leading corrections. So if you're in the field and you hear somebody talking about computing something to leading log precision or something like that, that's what they're talking about. So they're just, they've got this massive, loop diagram, and the easiest thing to extract are the logs. So you can take, masses to 0, push all that other crap away, and say, okay, here's my most important piece. It's the leading log. Okay. All right. But what about these logs, right? Aren't we in the massless limit? And if we're in the massless limit, those logs should be blowing up, right? Those S over M squared logs, okay? And the answer, so where I'm asking is, should we be concerned? And the answer is yes. Anytime you see stuff blowing up in your calculation, you should be concerned, okay? I mean, I believe in renormalization, but come on, you got to draw the line somewhere, right? Okay? And so what we'll do, hopefully, later today actually is get into the origin of these guys and how how we interpret them and what we do with them. Okay. So just to summarize, again, this process is computing a process to a higher order. You go ahead and when you get given the theory, you compute the exact propagator or as high as you can in perturbation theory. You compute the same thing, do the same thing for the vertices. You write down the tree level diagrams for whatever process you're interested in, and then you dress the point. Right? Everywhere you have a vertex, you put the blob, and everywhere you have an internal propagator, you put the blob. Okay? And those pieces you've already computed, so you can just plug them right in, like we did in that last part. Okay? All right, so the rest of these lecture notes has to do with something called the quantum action. And I'm not going to do that because I've got a massive headache and I don't feel like talking about the quantum action. So we're going to go ahead and skip ahead. It's kind of just a formal, it's just a formal way of doing all that stuff we just did. Okay. And I'm happy enough with where we're at. Okay. With that stuff. Okay. So let's take a 2-minute break and then I'll do this. Okay. I need a drink of water. Any questions on that stuff so far? No? Okay. All right, so now we're going to get down and figure out where these logs are coming from and what to do about them. Hopefully. Okay. All right, so let's go back and revisit where we were, okay? Now I'm using a different notation or way of drawing the diagrams, okay? But this is doing the same thing. So the circles are, again, the exact vertices, and when I have a double line, that means the exact vertex. Okay, so this should be the same stuff that I had before, but for some reason I use different. What do you call it when it's drawing? It's not notation, it would be.
It's notation.
Is it? Okay, all right. Okay, and.
It's all hieroglyphics.
Yeah, okay, yeah.
It's art.
Different.
Artistic.
I don't know what, I'm assuming he's correct when he says notation is correct, but I would have used like something like style or something.
Okay, that's the word I'm looking for, style. Just look at my Why do I ever listen to you?
I'm just saying that would be my personal preference, not that it's correct.
Yeah. All right. So we talked about how to compute that. You said if you want to do things exactly, or if you think the mass terms in your expressions are important, then you're going to have to resort to numerical techniques. But a lot of times, especially when you're interested in computing like jet cross sections or things like that, you can work in the massless limit. Okay. And when you work in the massless limit, you get really nice compact expressions, but there's no such thing as a free lunch, right? And so when you set n goes to 0, you run into some issues. All right? I won't call them problems. I'll just call them some issues. Okay. So we found that the one loop amplitude basically it always factorizes when you take this limit. It always factorizes into tree level amplitude times some correction factor. Okay. And so that's what we found. I don't know if I pointed it out. But here we have this one loop amplitude. It's a portion of the tree level amplitude. So here's the tree level piece, right? And this is the correction that we computed. Okay. And so we're left with that thing. Okay. With some order 1 corrections. All right. But we're interested in those large logs. Okay. All right. So for the time being, we swept that under the rug. Okay. I got inventive with my Google image searches here. So we kind of, we noticed those logs, but we said, let's just forget about them right now, okay? But let's try to look at them and see where they're coming from, okay? So we've seen, divergent behavior coming from the high energy spectrum, right? And these loops where we integrate and we hit the high energy spectrum and stuff starts blowing up, right? This is actually a low energy type of phenomena, and it's coming from taking the mass to 0, right? So it's low energy, right? And so kind of an analogy to what we call ultraviolet divergences. We call these guys infrared divergences. Okay? So they're coming from low energy parts of the correction. Okay? And so what we want to try to do is find the reason, the meaning behind the appearances of these logarithms and their subsequent divergences. And what we're going to do is we're going to ask ourselves, the one thing that we haven't really addressed is that we're computing a scattering process, and we're always assuming that we have perfect detectors, right? So we can always perfectly measure the energy of those particles in the final state. We can always exactly measure their positions, but we know we can't do that, right? First quantum mechanics tells us we can't do that. The other thing is, experimentalists can't build perfect detectors for whatever reason. I don't know, because of whatever, I don't know. Okay, so maybe the fact that we're finding these divergences, maybe it's somehow related to the fact that we haven't accounted for this yet. Okay, and so what we're going to ask is, if we account for that, if we put in these type of limitations, do these logarithms go away? Okay. All right. So like I said, real detectors have limitations, and it's not just due to the incompetence of experimentalists. Okay. It's real world. Okay.
It's because it's not a perfectly spherical detector in a vacuum.
Yeah. But even measuring things like energy, you can only measure it down to some threshold. There's always some threshold that you can't measure down to zero, right? And sometimes particles are going to be so close together that in your detector they're going to look like one particle, right? Because you just can't spatially resolve two particles that are very close to each other. Okay. Right. And so that's one case. So you have two cases here, right? You have a case where maybe you're producing extra particles besides the two that you're requiring it that you find two, right? But maybe in addition to those two, you're producing a third one, and that third one is just so low energy that you're not detecting it. Okay? Or maybe it's got high energy, but it's really close to one of your other particles. So in your detector, it looks like one particle, right? Okay. All right. So that's what we're asking is, if we include those processes, so we have something that looks like, well, I think it's on the next slide. But anyways, so we have a process that looks like this, right? We have one diagram that looks like that. So what I'm saying is, maybe we're emitting another particle, right? And this guy either has low energy or it's very close in the direction of this guy or this guy. Okay? All right, so that's what we're going to ask is, if we compute these corrections, right, in the low energy, where we take the limit of low energy or collinearity, I think is the word, of this guy, do those account for what we're seeing? Can it balance out? Can it cancel off these problematic logs? Okay. All right, so let's look at our phi process, the 2-to-2 process in our phi cube theory. So the the full amplitude we know is given by that blob. Okay, and what I want to do is consider the case where, so I don't care about what's going on in the blob. I'm just looking at the external light. Okay, so I'm going to consider this case where I have one particle that splits into two, or it's better say that it radiates or emits another phi particle. Okay, and so I'm going to define the momenta of this guy to be k, and the momenta of these two, k1 and k2. Right, and I know that when I sum up k1 and k2, I have to get k. Right. All right. So the amplitude that we can write for this guy is just basically the tree level, or this amplitude up there, times what? A propagator and times a vertex, right? So that's what I have here. I have the T from up there, a propagator, and a vertex, okay? And what we want to see is, if we take the massless limit, does this thing give us big logs, exploding logs. Okay? All right? My claim is that it can, or that it will, and what we're going to do now is see how that works. Okay? So we're going to do this. So we're going to compute the cross section, all right, for our 2-to-2 scattering. Okay, but this time we're going to account for the fact that maybe we have contributions like this. Okay, so this part gets a little confusing because I'm computing the total cross section, meaning I'm integrating over all final state momenta, right? But it's not really the total cross section because I'm going to leave out. I'm not going to integrate over one of the momenta. Okay? You know what I'm saying? So I've integrated. So if I look back at this diagram here, I'm integrating over this momentum, but I'm not integrating over this one yet. Okay? So that's why I only have one integration there. Okay? Because normally we square the momentum or square the amplitude and integrate over all final state momentum. All right, so I have one integration, okay? So that's what it would be for just the tree level diagram, that top guy. And for the split case, we would have the split amplitude squared, we'd have K1 and K2, and then there's some factor of 1/2, some symmetry factor, okay? And so we'd have to integrate over K1 and K2, right? And what we can do is we can write down the total cross section, or the total observed cross section, and it's going to be a sum over what we had computed before plus the split part, this part that's coming from these particles splitting. And now I can use a trick. Okay, so I have this dk here, I have this dk here, and here I have dk1 and dk2. So I can use a trick. I can insert 1 into that second term in the form of that mess, right? We showed earlier, or I don't know how long ago, that mess is equal to 1, okay? All right, so I can insert that, and this dk twiddle, remember, is that Lorentz invariant thing. So it's like dk over some factors of 2 pi, but it also has this 2 omega inside. Okay? So what that does is, when I insert that 1, it allows me to pull out this dk, right? Because I'll have a dk in this term now. And now I can get rid of that, right? Because it's on both sides, so I can imagine integrating over k on both sides, and it goes away, right? Okay. Right, and now I take, so I have here somewhere the split amplitude squared, right? So I take that from the previous slide, I plug it in, it gives me the g squared over the propagator squared times the t squared. So now I can pull t squared out. Okay, everybody with me so far? Yeah, okay. Now we want to ask ourselves, okay, so this is about as far as we can take it. Now let's take the massless limit and see what happens, okay? The denominator, okay, so let's first look at the denominator, okay? So k squared here is that total k, right? So I can write it as k1 plus k2 squared. So if I square this out, I get k1 squared plus k2 squared, and this is supposed to be 2k1 dot k2, right? But it's the formula of the dot product. Right? And remember that k, in terms of, because we're setting that thing, that constant thing, we're setting it to 1. So k has units of energy, so it goes like omega and the 3 vector omega. Right? So that means that I can write k squared, and I plug in these expressions, and I end up with something that looks like this. Right? Here's the cosine between omega 1 vector and omega 2 vector. Right? And I can simplify that, and I get down to something like this, okay? So in the massless limit, I've gone from, that denominator was k squared minus m squared, right? And I set the mass, take the mass to 0. This guy goes away, and what I'm left with is something that goes like 4 omega 1, omega 2, where these are the energies, right, times some sine squared, played over 2. Okay. Now we can see where we might get some divergent behavior, right? Because if these guys are what we call soft, if they have low energy, right, this thing's going to blow up, right? This term right here, right? Because if I take omega goes to 0, this is going to blow up. Also, I have a collinear type of divergence because when theta goes to 0, is that right? Theta, oh yeah, it's in the denominator. Sorry. When theta goes to 0, this goes to 0, and then blows up. Okay, so you can see just out of this this split diagram, you can see that there's some divergent behavior, right? And what we want to see is, are they of the same form that we ran into from those other guys, and do they somehow cancel them off? Right, that would be the dream scenario if that happens, right? Okay, so let's see what happens. All right. Okay, so I'm going back. Let's see where I am on this. Okay, so I've worked out what this guy is. Okay, now let's go back and look at these things. All right, what do they look like in the massless limit? Okay, so we can work in spherical coordinates. All right, and I can replace these dk1 and dk2 with this mess. All right, okay, and then I can plug that guy and that guy into our equation 9, which is that guy. All right. And what do I get? So if I plug that into that and I cancel some stuff off, I find that term, that second term, which went like dk1, dk2 over k squared, right? Because I took the mass to 0. Or if I see, it's this guy. So this thing, k squared, okay? And rewrote the integral, the integrals as that, and I get something that looks like this. And I've written it in d dimensions, okay? And so what you can see is that at the low end, where omega 1, omega 2 go to 0, you're going to have divergences for d less than or equal to 4. So in 4 dimensions, you're going to get soft divergences. Right? 6 dimensions, what happens? Those omega 1, omega 2 have negative exponents, so they go up to the top. Right? So in the low energy region, 6-dimensional theory doesn't have any soft divergences. But the collinear piece, which we've expanded using the small angle formula, right, diverges in the case for less than or equal to 6, dimensions less than or equal to 6. So we do have, from these splittings, we are going to have collinear divergences. Okay? We haven't computed their exact form yet, but we know that we're going to get these divergences. Okay? Right. And just to note that one way to regulate these guys is to just introduce mass. Right, keep the mass terms. Right, if I had kept the mass terms, I would have never known these guys were here. Right, everything would have been hunky dory. Okay, so there's always a way to cut these divergences off, and that's just introducing masses. Okay, but maybe you don't want to do that. Maybe you want to keep everything massless. Okay, so that's what I'm saying here is that these divergences are hopefully of the same form, and maybe they come with a minus sign, and we can cancel some stuff off. Okay. Okay. All right. Okay. So let's do this. All right. So let's assume that we have a real detector, and we're going to assume that this detector has real limitations. Right? And in particular, in 6 dimensions, we're going to have some angular threshold. Right, or I didn't know what to call it. Some angular limit to where we can tell particles apart. Okay, and so we're going to assume that it's the experimentalists are somewhat competent. Okay, so it's smaller than 1. Okay, but it's going to be much larger than m squared over k squared when I'm taking m to 0. Okay, so somewhere in between those two. Okay, so let's go back to equation 9. All right, I'm going back to the full thing now. All right, and when we integrate over the phase space, we can like it says, we can take this delta function to do one of these, or to do some of those integrations, right? And the angle that we're interested in is that theta angle. But the theta angle can be broken up into two pieces: the angle of K1 with respect to K, and the angle of K2 with respect to K. So we're calling this gamma. Okay. All right. And then for m equals 0, the magnitude of the 3 vector simplifies. We've seen that before. It's just square root of s over 2. Okay. So I can put all that stuff in. What am I doing? I'm using the expressions for the phase space measures of particle 1 and 2. I don't feel like going back to equation 7, but we get this. Okay. Where omega 4 is just 2 pi squared, and it's just the area of a unit 4 squared, 4 sphere. All right, so I have total energy over omega 1 and omega 2. I've got this magnitude of K1 to the 4th, and then some integrations still to be done. Okay, and you can work out the geometry of these guys, and you can see that K1 is a ratio of sine gamma over sine theta times the original K. And then K2 is the same thing except it's beta. And we're assuming here that all angles are small. Okay? So beta is small, gamma is small. Okay? And so what we can do is introduce some new parameter. I'm going to call it x. Okay? So I'm going to say beta is x times theta and gamma is 1 minus x times theta. Right? So if I add those two, I obviously get theta, right? Which is what I started with. Okay? And x is somewhere between 0 and 1. Because we're expecting it to be small. And again, we're assuming that theta is below our threshold. Okay, so theta is below whatever our limit is to the angle that we can measure. Okay, so now let's set the mass equal to 0. And what do we get? Well, when we work it out, the propagator piece gives me something that looks like that. Okay, so I get all this mess, okay, and what I've done is expanded to leading order in the mass, right, which we're taking to 0, and to leading order in theta, which explains that theta squared there, because we're assuming that theta is small, okay, and the function of x there is just some mess of functions of x's, okay. All right, so everywhere else we can safely set the mass equal to 0, right? So we get the energies in terms of x and magnitude of the 3 vector k, right? And then I can plug all that stuff back in, okay? And whatever equation 14 was, which was equation 9 originally, becomes this thing, right? So I've got some constants out in front. I've got some integration that I have to do over x. Right? This came from the phase space integration. And so I had to integrate over K1 and K2, right? But those are replaced with x times theta or x1 minus whatever. So that's how I get these integrations of x and theta. Okay, so these are the guys I have to do. And you note that the limit on this theta integration, the limits are 0 up to delta. Okay? And so I think I can do those integrals. Yeah. So I can do the theta integral, and look what I get. I get a log of some small quantity, delta squared, but times k squared over m squared, and then the other stuff. Okay. And then I can perform the x integral, and I end up with something that looks like this. Okay. So this is just the contribution from one diagram. So this is, I think it was only this guy that we considered, right? You actually have contributions from splittings off the other final leg, but you also have to consider splittings off of the initial legs, right? Because those will give you final state particles too. Okay? So it basically comes in, it's just a factor of 4. Right? And so what I get is this, right? So this is what we want to add to our one loop calculation, right? So remember we had that one loop calculation sitting there, and that's the thing that had those s over m squared logs, right? The big ones. Now we've gotten this thing, and we were hoping that we were going to be able to cancel off those logs from the virtual piece from these, what we call real corrections. Okay? And when we put it together, we get some cancellation, but it's not exact, right? And so what happens is when we take the virtual calculation and the real calculation, we add them together, we go from one big log to two big logs. All right, so unfortunately, we didn't get a cancellation, we actually made things worse. All right, so we've got this big log, which is the one that we originally had, but now we have a big log, and this one I'm blaming on experimentalists. Okay, so that's not our fault. Okay, but the problem is we have two large logarithms that we have to deal with. Okay. Yeah. Okay. So we have two large logarithms, and what we need to do is deal with those. Okay. And I don't know that I have those notes pulled up. I don't even remember what they're called. Oh, yeah, here we go. You know what? Actually, this is called a day because I haven't read over these notes. I want to make a fool of myself. All right? But we'll pick it up next time, and I promise you, we'll deal with those logarithms, those big logarithms, okay? And we'll get rid of them. All right? So like I said, on the midterm, if you can, just scan it and send it to me. And, the next couple of days is fine, okay? But if you have questions, and you're partially done or something, and you want to send me something, ask me something, go ahead. Because people have them. All right. So, okay. All right.
I got the question now. I'm almost